Hi. In recent years, data breaches such as the Facebook Cambridge Analytica scandal have increased awareness surrounding the protection of personal data and have brought to the forefront questions on how to implement the legal measures that have been put in place to enforce the privacy rights of individuals. One such regulation that took effect not so long ago is the Gdpr, which all organizations that handle EU resident personal data must comply with. But how does one evaluate compliance in a real-world system? First off, let me step back and give you a general overview of a works subject. The General Data Protection Regulation, or GDPR, was brought into effect in March of 2018 with the core purpose of regulating how organizations collect, handle and protect EU resident personal data, with hefty fines of up to 20 million or up to 4% of total revenue to be paid in cases of privacy violations. Proving compliance has become an important necessity. But analyzing a running system for evaluating its compliance is a hard problem. Therefore, we propose a methodology for designing an IoT system by embedding GDPR demands by design and querying the system for evaluating its compliance with the regulation. In order to prove GDPR compliance, an organization must extensively document the procedures involved in the processing of data and evaluate their lawfulness. They must be able to show how and where the personal data it holds is stored, secured, and processed. This can be done by keeping track of the interactions between its system's components and the data it processes on behalf of its users. In addition, an organization must be able to document proof of consent for the attainment and usage of the data. So, to aid us in the process of showcasing bare minimum compliance, the graph database company Neo4j proposes a set of fundamental questions related to GDPR articles. We utilize these questions for extracting compliance requirements and querying the system for evaluating its compliance. The problem thus boils down to how to design an IoT system that encompasses GDPR compliance requirements, for which we propose designing it by considering GDPR requirements and system functionality requirements represented as class diagrams, and representing the system as a graph that can be queried for evaluating its compliance. To show proof of concept, we demonstrate our solution in a remote patient monitoring system by utilizing UML for creating the class diagrams of the system design, and the property graph, a set of nodes and relationships with labels and properties that can be easily queried in a graph database. The remote patient monitoring system that we design involves personal data that is collected from wearable sensor devices, which are remotely transmitted to healthcare personnel. This system offers the advantages of reducing hospitalization costs, personalizing the healthcare process, and increasing patient autonomy. This system involves users, such as patients, who wear heart monitoring sensor devices that transmit biometric data to a service, doctors who subscribe to a number of patients in order to monitor their conditions and access their data, and administrators who have the highest data access privileges, as well as services such as sensor-related ones, for example, the device interface service that the devices transmit data to, storage-related devices, for example, the publish-subscribe service that notifies users upon value changes and communicates with a database that holds recently transmitted data, and security-related services, For example, the policy enforcement point proxies that implement access control policies to services based on user roles and access policies. After having defined the functional requirements of the system, what now remains is to create the system class diagram by incorporating GDPR requirements into the design. To do so, we incrementally construct the system's class diagram using UML with the help of the compliance questions we previously mentioned. We begin by introducing the fundamental entities, meaning the data owner and device entities directly related to personal data. We also defined the personal data entities that the system holds. These are user data, subscription data, and sensor data. Furthermore, regarding the storage entities of the data, we create 3 database classes signifying where each personal data entity is stored. Question 3, how and when was the data obtained, relates to information about the consent provided or revoked, at what time, and its type. For example, terms and conditions. Question 4, what is the need for this data, introduces the usage of data that a consent enables and the categories of events that process personal data. Examples of these are the data access and data export events. Question 5 involves which users have access to the personal data of other users. Whether the data owner provides consent to use the data does not introduce any new entities, but involves entities that we have already defined. The question of whether the data is secure relates to security mechanisms enforcing data protection, such as the ofthe and permission classes. It's worth noting that no encryption-related class is introduced here, since encryption is supported for all systems and devices by design. As in question 6, questions 8, how does the data travel through the systems? In question 9, does the data ever cross international borders, involve pre-existing entities? Finally, by combining the architecture entities and diagrams related to GDPR concepts, we derive the complete class diagram of the remote patient monitoring system. By using a simple UML to property graph mapping, we can easily transform the class diagram into a property graph. Each class is mapped onto a node, each association to a relationship. Each class name is represented by a node or relationship label, and each class attribute is mapped onto a property. The resulting graph, stored in a graph database, can then be queried for the purpose of evaluating compliance. In order to evaluate compliance on our system, we must answer each of the GDPR questions defined earlier. Each answer, represented as a property graph query, yields a distinct report that corresponds to the system's response to a specific GDPR compliance requirement. These reports can be formally analyzed by a DPO for evaluating compliance. Here, we show 3 example reports for questions 1, 3, and 8. It must be noted that in these examples, we have queried the domain graph. In a more realistic scenario, the system should be instantiated with real data, so a DPO who inspects the reports can be informed on the specifics involving the personal data being held and processed. So the query for question 1, what data do you have, results in personal data entities and the persons they belong to, as you can see. How and when the data was obtained reports information regarding the user or device fundamental data entity each personal data node is related to, as well as the consent that the data owner has provided, with extra information such as time of consent creation, consent type, and time of consent provision. In the case where one of the consent information fields, let's say consent type or time of provision, is undocumented or incomplete, DPO might deem the keeping of such data as unlawful, which would violate GDPR consent requirements. Answering how the data travels through our systems yields descriptions of each consent or data process event. For example, consent types and data usages related to data movements between systems, let's say databases, and to the time each event occurred. For example, the first entry contains a consent event of a person related to a personal data node of theirs that was revoked at a specific point in time, providing key insight into how, when, and where data flows in the system plays a crucial role towards meeting GDPR compliance demands. All in all, our work favors ease in applicability and at the moment lacks in vigorous quantification of the whole breadth of the GDPR legal text. By focusing instead on a set of cornerstone requirements, we demonstrate a methodology for achieving compliance evaluation for IoT applications of reasonable complexity. Since it is work at an initial phase, there are still some interesting aspects that can be addressed in the future. Such are improving adherence to data protection principles and making use of technologies borrowed from the semantic web. Any questions? Thanks for listening.